Hi, my name is Fuxin Li from Oregon State University. Today I'm going to talk about our work on point cloud convolution. We start with point cloud convolution. At a neighborhood with a center point P0 and its features F0, point convolution seeks to aggregate features from its neighborhood by learning a multilayer perceptron on the relative coordinates between each point and the center and use that as a weight function to aggregate the features of the neighborhood. It can be used to build deep networks for a number of tasks, such as classification and segmentation. In point cloud convolution networks, there are usually two ways to choose the neighborhood. The first one, k-nearest neighbors, ensures every point gets the same amount of neighbors. However, this neighborhood may get very irregular, as certain points may be much further away to the center than other points. The other approach, epsilon ball, to choose the neighborhood, ensures all the points are within an epsilon distance to the center. However, it generates an unequal number of neighbors and in practice requires padding to bring all the neighborhood to the same size, which leads to more computational and memory waste. Besides, when we do a speed comparison, we can see that k-nearest neighborhoods are usually 2 to 4 times faster. Because of this, we would like to be able to use k-nearest neighbors as a neighborhood choice. However, k-nearest neighborhoods are not very robust. As one can see, if we just simply change the point sampling rate, then the size and the shape of the k-nearest neighborhood would change significantly. This may also happen between training and testing neighborhoods, and thus negatively affect recognition and segmentation performance. Our idea is that we could incorporate viewpoint invariance to improve robustness to the k-nearest neighborhoods. We propose a viewpoint invariant coordinate transform to point cloud convolution, which serves two purposes. When the weights and features are both invariant, we can achieve complete rotation invariance without any training time data augmentation. On the other hand, when complete invariance is not needed in realistic cases, we make significant improvements on performance and robustness by making network invariance aware. We can use this to generalize to unseen scales and rotations at testing time. So the main idea of the paper is to, instead of using the Euclidean relative coordinates pi minus p0, we would use a number of angles and norms which we can make to be invariant to rotations and scale. In terms of feature invariance, instead of using the regular XYZ feature, we could use principal curvatures to make them to be invariant. Our first experiment is on ModelNet 40, where we showed that our approach does not need any training augmentation, yet can generalize to unseen augmentations at testing time and outperform all previous approaches that actually need training time data augmentation. On the realistic indoor ScanNet dataset, we show that by making the weights invariance aware, which uses both viewpoint invariant coordinates as well as the non-invariant coordinates, our approach can significantly outperform previous approaches and also be significantly more robust to test time downsamplings, which means testing at an unseen scale. We have also observed similar improvements on outdoor semantic segmentation dataset, SemanticKITTI. To learn more, please check our poster. Thank you very much.